time for lunch. My name is Nováková. I'm an evolutionary biologist from the Charles University in Prague and also a science fiction writer and translator. But today, we are not going to talk about me. We're going to talk about her, Venus. And nowadays, we know that under its impenetrable cloud layer, we can find really hellish conditions. There is more than 90 atmospheres pressure and more than 460 degrees Celsius. Nothing at all that we know of could survive on the surface of Venus. But these are quite new pieces of knowledge that we only gained in the 60s, in the last century. And in fact, for quite a long time, people thought that what is hidden beneath Venus's clouds is actually something entirely different. And ever since the advent of astronomy, people thought that Venus might have life or that it could harbor some alien civilizations. And these thoughts can be summed up quite nicely in the words of one of the first science communicators, as we would call him now, Camille de Flammarion, and in his Le Pluralité du Monde Habité, or the plurality of habitable worlds, he said that if Venus were without population, then the Earth must be similarly lacking. And reciprocally, if the Earth were populated, Venus must be populated also. Well, we can see the biases in his reasoning, but this kind of analogical thinking was quite common in early science, and sometimes we can also meet with it today. And Flammarion wasn't the only one thinking in these lines of thoughts, and actually this picture is from his book and it's his own illustration of how it might look on the surface of Venus. And this is a bit newer map of Venus. Now, we might be wondering, how could anyone draw a map of Venus when we can't see anything beneath these clouds? But actually, our pattern recognition can sometimes play tricks on us. And maps of Venus have been drawn from the 17th century up to late 19th century. And this map has been drawn at that time by the famous science supporter Percival Lowell. He was a rich American entrepreneur, we'd say today, and he supported astronomy research, and he was also a big proponent of the idea of different civilizations in our own system. You might recall the affair of the canals on Mars, and actually when Schiaparelli, the Italian astronomer, observed what he thought there were channels on Mars, natural channels, it got translated into English as canals, which implied artificial origin, and Lowell got it as an argument for a civilization on Mars, and he also thought there might be some civilizations on Venus. And his mind, his pattern recognition played these tricks on him that he has drawn what he thought he was seeing, even though he was only seeing different patterns in the clouds of Venus. So these maps are interesting as a historical lecture on how science should not be conducted, but they bear no relevance whatsoever on the real surface of Venus. And we learned more about the real conditions much, much later, and that allowed for thoughts of a lush tropical Venus to flourish. This is an illustration of how it might have looked on Earth during the Carbon epoch. And actually, lots of people in the late 19th century and early 20th century thought that Venus must resemble Carboniferous Earth with its swamps and forests and high humidity. And also lots of pulp fiction was based on these thoughts. We got the golden Amazons of Venus and dinosaurs on Venus, and authors like Edgar Rice Burroughs or Isaac Asimov or many other well-known science fiction authors wrote stories set on Venus and in its great lush forests. And of course, there were lots of thoughts about Venusian civilizations before. And for example, the philosopher Bernard de Fontenelle, already in the 17th century, said that since Venus is closer to the sun, then the inhabitants must be scorched by the sun, and they must be very amorous and witty and active. And Immanuel Kant, the well-known philosopher, thought that intelligence must be increasing with the increasing distance from the sun, so that the inhabitants of Venus might resemble apes to us, but we might resemble apes to the inhabitants of Jupiter, and so on. There were lots of these thoughts in the 17th and 18th century, and the pulp science fiction has borrowed a lot of these tropes. And in the early 20th century, lots of scientists thought that Venus actually might be habitable, although they largely discouraged the idea of a Venusian civilization. This is Svante Arrhenius. He's a well-known Scandinavian scientist, and he was one of the first people who noticed the climate change. And he thought that a great deal of the surface of Venus must be covered with swamps, and also that the clouds mean there are uniform climatic conditions on the planet, and there must be low forms of life, and they're similar all around the planet. And the British astronomer Charles Abbot thought that the reflecting power of the clouds seems to show that Venus is a moist, humid place, and that it has almost identical temperatures to Earth, and that it appears lacking no essential factors in terms of its habitability. Also, at the time, we didn't know the rotational period of Venus, because although Venus is often referred to as the sister planet to Earth, because it has almost identical size and composition, it's actually a very different world, and not just in terms of its current surface conditions, but also, for example, the rotation. Because Venus rotates around its axis for more than 240 days, which is actually longer than the Venusian year. And if they knew it at that time, they might have been more reserved about the claims of Venus's habitability. And in the 1962, we discovered what a lot of scientists have suspected since the 30s and 40s, that Venus is nothing like the tropical forests or swamps, that it's actually quite hellish place. This is an illustration of the Mariner 2. It's a NASA spacecraft that made a flyby of Venus in 1962. And the measured temperature and thickness of the atmosphere shows that the conditions on the surface of Venus resemble nothing like Earth. And subsequent missions only confirmed that notion. In 1967, there was another Mariner spacecraft and also the first Venera flyby. And especially Russians had a lot of success with Venus, and this is a stamp commemorating the Venera missions. At first there were flybys, then orbiters, and then there were also landers, which for the first time enabled us to see the surface of Venus in the 1970s. These are the images of the couple of first Venera landers, and they show quite large plains covered with small boulders, and they resemble Earth deserts. They are desolate places where nothing could possibly live, and the surface measurements also showed that it's correct that Venus has more than 460 degrees Celsius temperature on the surface, and that the pressure is also very high. The Venera landers usually lasted about 1 hour on the surface before the transmissions just stopped. And it's one of the most adversary environments to send our spacecraft to in our solar system. But although we had some of the surface images and we had data from the orbiters and from cloud balloon probes like in the Pioneer Venus mission by NASA or the Vega missions by the Soviets and French, we still knew quite little about the surface of Venus. And that was changed in the 1990s by NASA's Magellan probe, which mapped the whole surface of Venus by radar imaging, because we can see nothing of the surface in visible light, but radar is capable of penetrating the clouds and reflecting off the surface and showing us how it looks like. And this is sort of a map of Venus compiled from the Magellan images. And a lot of things surprised us from them. For example, the large number of volcanoes on Venus. It seems to be a very volcanically active place. We can see a large volcano field on this image. And these are the so-called pancakes. These kind of volcanoes don't exist on Earth, but in the Venusian conditions of the higher pressure and temperature, it's possible that some mental hotspots can reach to the surface and sort of break through and create these pancakes. And there are also the so-called ticks and cobwebs. We can see a cobweb-like feature here. And they are probably created by a very long-lasting lava flows, which don't cool so quickly on the surface of Venus as they would on the surface of Earth. But the question stands, how did we get from a place probably like this to a hell like this? And in 1988, an American professor, James Casting, created a climate model which attempted to answer this long-standing question. And he calculated the illumination of early Venus by the early sun, which has lower luminosity than it has now. And he found out that it was directly on the threshold of staying, let's say, habitable place like our Earth is, and on entering the runaway greenhouse effect, which has happened at some point during Venus's history. Because if we illuminate the world a lot, then the temperature rises and the oceans start evaporating even more. Water enters the atmosphere. And even though most of us might not realize it right away, water is a very powerful greenhouse gas. It's more powerful than, for example, carbon dioxide or methane, and these play the largest role in warming Earth. But actually, if Earth had a high percentage of water in its atmosphere, then the warming would be even higher than it is currently. And this is likely what happens to Venus. Basically, if we evaporate a large enough fraction of the oceans, then the greenhouse effect raises the temperatures even more, which leads to even more evaporation. And we end up with a very thick atmosphere composed largely of water vapor. And then the water is dissolved by the solar wind and the UV radiation into hydrogen and oxygen. Hydrogen is a light gas. It doesn't have any trouble reaching the escape velocity and being carried away from the planet by the solar wind. Oxygen can stay a little longer. It can oxidize the surface. A part of it can also be carried away. But when we reach the point when the planet is very dry and it doesn't have the oceans anymore, but it still has some vapor in the atmosphere, it can start having more carbon dioxide because it's expelled, for example, by volcanic activity, which we presume was quite high in early Earth and early Venus. And without water, there are no effective geochemical cycles to help us recycle the carbon dioxide back into the water and into the rocks. Also, water is very important for plate tectonics. It lowers the melting temperature of the rock so that plate tectonics can happen. If Earth was without water, we might not have plate tectonics at all. And we don't know if Venus had it in the past. It certainly doesn't have anything resembling plate tectonics now. And when the carbon dioxide cannot be effectively recycled back from the atmosphere, it has higher and higher proportion in there, and it warms the world even more, so that we can transition from a water greenhouse into a carbon dioxide greenhouse. And this is what happened on Venus. But we don't know when exactly did it happen. There are actually many hypotheses trying to explain that. One possibility is that Venus never had any liquid water oceans. It's possible that the greenhouse effect kicked off really after the first primordial vapor atmosphere that even Earth probably had at the beginning, largely composed of water vapor. And it's also possible that it kicked off after some 700 million years after the planet's formation, which is what the casting's first model says. But there are many other models, and some of them put the moment, the threshold, when the runaway greenhouse starts 2 billion years after Venus's formation, or perhaps even later. And that will be, of course, very interesting for us, because there is a vague possibility that Venus might have had liquid water oceans for 2 billion years. And that is more than enough time for life to develop. The first traces of life on Earth come approximately from 3.7 billion years in the past, so that less than 1 billion years after the planet's formation. And it's possible that life started even earlier, but we don't have any old enough rocks so that we could find fossils of bacteria in them, and we don't have enough samples to test for different isotopic ratios, because life prefers to incorporate carbon-12 in its biomolecules, whereas higher, more heavy isotopes of carbon are not incorporated so much. So that if we find a distorted ratio of carbon dioxides, carbon isotopes in favor of carbon-12, we can say with some reliability that these samples have been a part of some life in the past. And it's actually one of the things we want to search for on Mars in future missions like the ExoMars rover or the Mars 2020 rover. But back to Venus, it had more than enough time to form life. But we don't know its history in much detail, and actually there are lots of unanswered questions. One of them is how large has the volcanism been in its history? Could it have prevented life even in the distant past? Or did it resurface Venus more than one time? Because if we look at a map like this, which is a map of impact craters on the surface of Venus, and we compare it to other bodies like the Moon or Mercury, we can say that there are much fewer impact craters on Venus than on these other bodies. And there is also different distribution of crater sizes. And of course, there is one quite simple explanation for that, and some of you may have already thought about it. Why do you think that Venus would have fewer craters than bodies like the Moon or Mercury? Yes?
They've been filled up by volcanic activity?
Yes, that is one possibility. The other is simply its thick atmosphere, because any smaller bodies entering it would burn up in it and they wouldn't hit the surface. And We can compare it also with crater distributions on Earth. But on Earth, it's quite tricky because we have plate tectonics, we have volcanism, we have oceans, and all of these activities erase the cratering history of the surface. And if we try to calculate the average age of Earth's surface based on crater dating, it's some 700 million years. So it's quite young compared to most bodies in our solar system. And actually, it's about the same for Venus. And the atmosphere isn't a sufficient explanation for that. And we can also see that the crater distribution is quite equal across different parts of the surface. And that suggests that not only there is some volcanic activity that could have erased the craters, but it could have been global. And it's probable that Venus has undergone a rapid, catastrophic resurfacing by large extent volcanism sometime in the past, maybe 600 million, maybe 700 million years in the past. And we don't know if that's the only time a catastrophe like this happened. If it was more frequent in Venus's history, then the chances of any life in the past would drop significantly, because it's hard to imagine anything surviving a complete planetary resurfacing like this. So the questions are unceasing. We don't know how long did Venus have any liquid water oceans, if at all. We don't know whether it had plate tectonics, which would enable more rapid geochemical cycles, enabling life to exist there like it does on Earth. We don't know whether it had conditions for life at any point in its history. Even though there were many missions to Venus, like Mariners, like Veneras and Vigas, like the Pioneer Venus, Magellan, or more recently ESA's Venus Express and JAXA's Akatsuki, which is on Venus's orbit right now. It's hard to answer these questions, and to be able to pinpoint the different points of Venusian history in more detail, you would have to send missions to the surface, and preferably missions that would last more than 1 hour there. Of course, it's not impossible, and there are many concepts for such missions. For example, the American scientist and science fiction writer Jeffrey Landis, you might have read some of his short stories or poetry. He put together a concept for a Venus land sailing rover, which uses very simple heat-resistant electronics, and it doesn't have any complex propulsion systems, because it would use the wind on the surface of Venus, which is very low, very slow. But with the thick atmosphere, it would be enough to propel the rover for, let's say, 1 or 2 meters a day, which is better than nothing. And it could thus sample the rocks on different places and try to find out, for example, if there are any old rocks that appear to be water-altered. There is a process called serpentinization. It's basically an interaction of rock and water, creating things that life might use, such as molecular hydrogen. Many, for example, methanogens in Earth oceans on the bottom of the sea use it to maintain their metabolism. And it also raises the temperature. It's an exothermic reaction. So we don't need any very special conditions beside some particular rocks and water. And it can create conditions for life. And it can also create minerals such as the serpentinite that are very long-lasting. And if we discovered them or similar minerals on the surface of Venus, then we would be reasonably sure that it had water and rock interaction at some point in the past. And we might try to do radiometric dating of these samples to find out when exactly it happened. So future missions might tell us more about these questions and try to answer them. Unfortunately, Venus's history is, as of now, a big mystery. And as to the chances of life, I have already hinted at the possibilities in the past of Venus. If it had liquid water oceans, it's quite likely that there might have been good prebiotic conditions. And here is a timeline from one of the papers suggesting that it could have had water oceans for more than 2 billion years. These are by Greenspoon and Bullock. Other scientists, such as Casting, are more pessimistic about this. And so we'll see. And one possibility of finding out whether Venus could have had any life in the past is to look for Venusian meteorites. Now, here on Earth, we have lots of meteorites from Mars. There are currently more than 130 meteorites that we know of that they came from Mars. And of course, it's easier for any ejecta from impacts to be carried to the deeper gravity well, so from Mars to Earth, from Earth to Venus, and etc. But it also goes the other direction, although not so much. And there's a good possibility that when we explore Mars to a greater extent, we will find out some meteorites that have come there from Earth. And they might tell us more about Earth history. We might find some fossils of old Earth life there. It's a very exciting possibility. And similarly, we might try to search for Venusian meteorites across the inner solar system. Of course, it's tough for any ejecta to actually reach the escape velocity if they have to come through the very thick atmosphere Venus has as of now. But if it had a thinner atmosphere in the past, let's say those 2 billion years ago, it would have been more possible, but it's of course hard to search for these particular meteorites. Maybe if we sample more near-Earth asteroids or sample Mars surface, we might be able to find some, but it will be very difficult, and it's possible that we will find none. But what about chances of life in the present? Actually, let me go back to this diagram, which is the Venusian atmosphere as it is now. And we can see that on the surface, the temperatures are very high. Here in Celsius, so over 400 Celsius, and it's more than 800 Fahrenheit. It's clear, the wind is quite slow near the surface. It's about 1 meter per second, but it's enough to propel the rover if we send it there. And as we go higher, we can see that the temperature is lower. And between some 48 kilometers and some 68 kilometers height in the atmosphere, we can actually encounter conditions that are very similar to the surface of Earth. The temperatures range between some 50 degrees Celsius to minus 30 degrees Celsius, which is all quite good for Earth life. And the pressure is around 1 atmosphere, so similar to what we are breathing now. Of course, the atmospheric composition is very different. Most of the atmosphere of Venus is carbon dioxide, and then there is nitrogen, molecular. We have lots of different sulfur compounds in the atmosphere, for example, sulfur dioxide. And there is also some sulfuric acid in these clouds. They are composed some 60% of sulfuric acid and 40% of water droplets. So there's still some water on Venus, although it's high above the surface and it's still very scarce. But we can think of some organisms that could be capable of withstanding these conditions, these high acidity, low water availability, of course, the difficulties of obtaining biogenic elements, and high UV radiation because we are closer to the sun and there is no ozone layer or magnetic field that could protect us against part of the radiation. And actually, we know of quite a lot of Earth extremophile microbes that could be capable of surviving exactly these conditions. One of these is this little bug called Cyanidium caldarium. It's a photosynthetic microbe, so it gains energy from sunlight, and it can survive with quite little water, and it has some ingenious metabolic pathways to survive in acidic environments, etc. And as to the obtaining of biogenic elements, well, carbon is not a problem. There's a lot of carbon in Venusian atmosphere. Sulfur is also not a big problem, nor is oxygen. Hydrogen can be harvested from the water or from the sulfuric acid. Nitrogen is also there, and if it was able to isolate molecule nitrogen from the atmosphere, similarly to some bacteria on Earth that are capable of doing that, it also wouldn't be any big trouble. Now, phosphorus might be a problem, but then again, there are acids of phosphorus in the clouds of Venus that it could also utilize. So we have all the basic biogenic elements right there. And moreover, the conditions in the cloud layer are very stable across time. Not only does the temperature and pressure stay basically the same all the time, also the wind patterns are such that any particles that are in the cloud layer would stay there quite safely for months, if not years. It's not like Earth's atmosphere when if there are some microbes carried off the surface by wind and carried to the higher troposphere or even stratosphere, they pretty quickly fall back to the surface of Earth, and it's a quite unstable environment. On Venus, this might be much easier. And as to the UV radiation, there are ways to protect against it. Also, many microbes are capable of repairing damage in their DNA quite ingeniously. One of the most resistant is, for example, the famous Deinococcus radiodurans. He is sometimes called the Conan of bacteria. And there are also things you might utilize as shields against UV. And actually, in the cloud layer, there are 3 types of particles based on their size, and the largest ones have some 10 microns or more, which is similar to the size of some bacteria. And these particles are likely composed of polymeric sulfur. And sulfur polymers are quite good for protecting against ultraviolet radiation. So we don't know if these are just geologically and atmospherically created compounds, or if there could be some life utilizing them for protection. But it could be quite easy to test for it. All that we need to do would be to send probes in the cloud layer, for example, balloon probes, or maybe some planes that would harvest solar energy, and they would have equipment searching for life, such as Raman spectrometers, which could tell us a lot about the detailed molecular composition that we might encounter there. We might measure the carbon isotopes, as I talked about previously. They might also search for signs of biogenic molecules similar to what we know from Earth, for example, the nucleic acids, or some lipopolysaccharides, or amino acids. For example, if they are chiral, left-sided or right-sided, we can search for complex sugars, etc. There are many different ways to test for the presence of life. So it seems there is a good possibility that life might exist in the cloud layer of Venus. It looks almost balmy in comparison to some Earth environments. Well, actually, there is a little problem with that, because, as I mentioned before, Venus have undergone at least one catastrophic resurfacing some 700 million years in the past. And in this resurfacing, the atmospheric composition and the cloud layer would change a lot, because all the volcanism would release many volcanic gases in the atmosphere, not just carbon dioxide and sulfur dioxide, but many more, even methane. So the conditions might have been very different in a not so long ago past. And it's difficult to imagine life that would survive them. Basically, any life we might expect on Venus today in the cloud layer would have to be quite hardy, because it would have probably evolved in the oceans of Venus when it still had them. Then it might have transitioned into the atmosphere and adapted to the atmospheric conditions. But these conditions probably changed a lot during Venus's history. So even though it's not impossible for life to exist there, these are pretty big obstacles, bigger than these ones I have just mentioned. But again, missions sent to the cloud layer might resolve this question once and for all. And just for fun, there have been some batshit crazy variety of hypotheses of Venusian life. And for example, one Russian scientist recently claimed that he saw macroscopic life forms in the Venera images, and he named them bears and millipedes and such. And when he didn't arrive, as he planned to last European Planetary Science Conference in Nantes last year, then his poster was sort of added by the conference attendees. It's part funny, part sad, but yeah. And just before we end, there have also been some prospects of terraforming Venus to enable future Earth-similar life there. And actually, the scientist and science communicator Carl Sagan offered the possibility of terraforming Venus in the late 60s. And he proposed sending algae into the clouds that would be able to use the carbon dioxide, produce oxygen, and by harvesting the carbon dioxide, lower the greenhouse effect and make the surface better suited to habitability in the future in, let's say, hundreds of years. After a few years, he retracted these claims because at that time he didn't know how thick the atmosphere was. At the end of the 60s, it was still presumed that it might have been of several atmospheres pressure on the surface, but no one expected it to have 92 bars, 92 atmospheres on the surface, as we know it has now. And it would be virtually impossible to terraform such a world the way Sagan proposed. There have been some science fiction options for that, and for example, in Kim Stanley Robinson's 2312, humans have put a large sun shield before Venus so that the atmosphere would collapse, and then they harvested the carbon dioxide and carried it off the surface to make the planet more habitable. But if it ever happens, if it is possible, it's hundreds of years, if not millennia, in the future. And in the meantime, we might also change our way of looking at Venus, for example. If there's a lot of things to learn about its history, and consequently about the history and future of Earth and other planets, or if Venus by any chance has life in the cloud layer, then it might not be ethical or scientifically sound to try to terraform the world. And just before we end, Venus can tell us also a lot of things about the possibilities of life on other worlds. You might recall that when I was counting the history of Venus, I mentioned the period when it had a lot of water vapor in the atmosphere, but it was dissociated by radiation into hydrogen and oxygen, and hydrogen is more likely to escape. Now, if we are talking about detecting biosignatures, some indicators of life on extrasolar planets, what is the molecule we think about first? Yes, it's water, but again, we have detected water in many atmospheres, but these are very hot and very thick, some hot Neptunes, hot Jupiters, so water is not really a good indicator. But many people also think of oxygen. Here on Earth, it's an indicator of life. It's produced by photosynthesis. We wouldn't have it in the atmosphere if it wasn't constantly produced by life. So we want to look for the presence of oxygen on other worlds. But it's also possible that if we detect large fraction of oxygen in the atmosphere of an Earth-sized extrasolar planet, it might be too early to get happy about finding a second Earth, because we might be finding a second early Venus. So we have to bear this in mind, and of course, when we are looking for biosignatures, just one of them isn't reliable to say if there is life or not. And if we, for example, detected a large fraction of oxygen and some methane in the atmosphere, now that would be good, because the oxygen would basically react with the methane and get it off the atmosphere. So it also has to be constantly added by processes in life, such as it is on Earth. But here on Earth, although we have oxygen and methane in the atmosphere, the fraction of methane is too low to be detectable from other solar systems with the technologies we have right now. So we would have to find a planet with a larger proportion of methane in its atmosphere if we were to say there is life. But this is just to say that Venus can tell us a lot of secrets, not about its own history, not only about extrasolar planets and chances of finding life there, but also of the Earth's future, because as the sun warms up in its stellar evolution, then the Earth will also be warming. And while geochemical cycles might damp the warming a little, still in 1 billion, 2 billion years, Earth would be uninhabitable for complex life, such as we are. And the history of Venus could tell us when exactly this might happen and how. So before we have a little time for questions, I would like to conclude with that Venus will reveal its great secrets, not only about its own history, but also about Earth's possible future and the fate of other sun's worlds. Thank you for your attention. So we have some 2 minutes for questions. Is there any? If there is no question at this time and you think of some in the future, you might email me on this address. And if you want to learn more about interesting stuff across the solar system and beyond, or science fiction set in the solar system and beyond, you can visit my website here. So, thank you.